right? So we don't see any gaseous ones, right? Because to get to the vaporization temperature for this, you'd get to such a high temperature that you'd probably destroy the molecule before it gets to that point. You'd probably start to ionize the molecule, right? So there's no gases because the vaporization temperature is a lot higher than the degradation temperature is for the fatty acids. And it makes sense, right? If you start to burn butter, right, it doesn't turn to gas. What happens before it turns to gas? It turns brown, right? And you burn it, and you basically just turn into carbon charcoal, right? So that's the different properties and different classifications of the fatty acids based off their melt point. So why did saturated hydrocarbons have higher melting points? Yeah, the molecules can be closer to each other, so they can maximize the London dispersion force interactions, right? And it's because the saturated or the unsaturated fatty acids, those carbon chains, they have double bonds. And what does that do to the double bond? It gives it an irregular shape that makes it harder for the molecules to then pack together, right? So it's harder for them to get close and feel those London dispersion forces, right? So these are going to be like a polar head, and then saturated is going to be a straight line, whereas a double bonded structure might have a kink in it because of the double bond, right? And that depends on the configuration of the double bond, if it's trans or a cis configuration. But in general, the unsaturated fatty acids are going to have lower melting points and more likely to be liquid at room temperature. Okay, and then we talked about the formation of micelles. You saw the emulsifiers in lab, and that's kind of where we left off. All right, any questions on any of that? Okay. So next we'll talk about fats and oils. And so these are going to be the most abundant lipids in nature. And there's going to be a difference between natural and artificial fats and oils. So when we say a fat versus an oil, what do you guys think of the difference between those two? Like if you in just everyday life, we're not even thinking about molecules, right? What's the difference if you think of something that's a fat versus something that's an oil? So they can technically actually both be from plants or animals. Most fats are going to be from animals, though actually, now that you say that, I don't know if there actually is going to be any plants that make any fats, but you can get oils. But if you let's think about, so I'll actually have to look into that to see if there are any plants that produce any fats. But if we think about the state of matter, what do you think of, like a fat versus an oil?
Physical.
It's physical state of matter, so like solid liquids and stuff. What do you guys think of when you think of oils versus fats?
One is solid and
Yeah, so basically a fat is just going to be a solid at room temp, and then an oil is going to be a liquid at room temp. All right, so that's the classification of how we determine fats and oils. Really what it is they're the same type of molecule. It's just the properties of what make up the molecules that give us the difference between the two. And so we actually did this when we made soap. We dealt with a fat, right? So a soap was just, what was a soap in terms of chemistry? How would we define what a soap was? Yeah, it was a salt fatty acid, right? A fatty acid salt is what it was. Right, we raise the pH of a solution. That does what to the carboxylic acid group? Yep, it makes it deprotonated, right? Because pH is lower than the pH is higher than the pKa, right? So it deprotonates it. You coordinate that with a, counterion like sodium or something like that. That creates a salt, and that's what makes soap. Okay, and so based off of the fatty acids that are in the fats and oils, that's what gives it the property. But that's how we distinguish between fats and oils usually. And so they're usually called, does anyone remember what they were called when we made soap? So that's what we did to make them, and that is one of the reactions that lipids will go through is a sapon, right? That was one of the classifications, saponifiable versus non-saponifiable lipids, right? Can they go through saponification, which was just base catalyzed. Remember, it's base catalyzed. Saponification is a type of what reaction? Hydrolysis, right? So it's base catalyzed hydrolysis, right? Why? Because in the reaction, what do we have to consume? Water, right? So we have to consume water in the reaction. So that's not just true for lipids. That happens in carbohydrates, amino acids and proteins, and enzymes, and for lipids. And so these are going to be called triglycerols or triglycerides. And the reason they're called that is because it's an ester that's formed between a glycerol and a trihydroxy alcohol and a fatty acid, or 3 different fatty acids usually, right? So if we think about what is a trihydroxy alcohol going to look like, right? So I know it's like, we talked about alcohols a while ago, and even when I hear like trihydroxy or whatever, it doesn't register in my brain what exactly it is that I'm looking about. But if we think about it, if we just break down the name trihydroxy, yeah, right, so trihydroxy, there's 3 hydroxy OH on the alcohol. And usually it's going to be on a 3-carbon chain, and so a trihydroxy just looks something like this. I'm going to draw this how I usually draw it. H2C, H, H2, COH, right? Carbon still needs to have how many bonds? 4, right? So the terminal carbons are going to have 2 hydrogens, the central carbon is going to have 1 hydrogen, and there's a hydroxy on each of them. And so these get added with 3 fatty acids. To then form esters, right? So this would be an esterification reaction. Esterification reaction is, how would we classify that reaction? Take one smaller molecules and make a bigger molecule. Condensation reaction, right? This is a type of condensation reaction. And what's the byproduct going to be in this reaction? Water, right? So this should be water, right? So this is going to go to a triglycerol, is what this molecule is going to be called. So it's going to be O, C, double bond O, C, double bond O, O, C, double bond O, and then the rest of the fatty acids, right? And then we get, how many water molecules are we going to get as a byproduct of this reaction? 3, right? Because for each ester that we formed, we required basically the deprotonation of the alcohol and the hydroxy group on the carboxylic acid, and then we also lost one of the oxygens as well. All right, so if I just highlight what I mean by that, right, when we combine these, this OH and where this OH are, they come together, and we lose 2 H's and 1 O in this case. The specific mechanism is a little bit more complicated. We're not worried about the mechanism, right? But we think about what we ended with, right? This was where the hydroxy group was on the trihydroxy alcohol, and then this was where the carboxylic acid was on the fatty acid, right? So when they come together, we have to get rid of some stuff that's already there, which would be 2 protons and an oxygen. All right, so this is an esterification, and this is going to be a condensation to form a triglycerol. Right, so this was a condensation reaction. And so natural triglycerides are going to be different from synthetic triglycerides because they don't have a single fatty acid that is at every spot on the triglycerol. Right, so we see that with the trihydroxy alcohol here, which is these spots right here, there's 3 spots for fatty acid to go through an esterification or condensation reaction. So if you think you're in solution, right, there's a bunch of fatty acids floating around. There really isn't going to be a natural selection to have all of them bind to one molecule. You're going to be just having a reaction with whichever fatty acid comes in contact with you. There may be some complicated things you can do to the fatty acids to get that type of selectivity, but But naturally in the body, if there's a mixture of fatty acids floating around, the triglycerol is going to form from random fatty acids that are in solution. So in a natural triglyceride, that means that you're going to have a different fatty acid at each spot on the trihydroxy alcohol. Right, so, and I'll go on the next slide, I'll talk about like a general way to write the triglycerol that's a little bit easier to interpret than, drawing the full structure for these. And then this last one is what we talked about when we first started talking about this, is solid triglycerols at room temperature are called what? So this isn't going to have to, has to do with the saturation of the fatty acids, right? But these specific lipids are in the category of fats and oils, right? So we're talking about in reference to fats and oils here. Solid ones are called what? Fats. And liquids at room temperature are called oils, right? Okay, any questions on this? Give you guys a last second writing. And then we'll talk. So a simple diagram for triglycerides is we're going to have what holds all the fatty acids together. What's the molecule that holds all of them together? Yeah, it was the trihydroxy alcohol or the glycerol, right? So that was the trihydroxy alcohol, or we also call that the glycerol. And how many fatty acids could we have on a single glycerol? 3, right? Because trihydroxy, each of the OH groups is where the esterification happens, right? So there's going to be 3 spots for each fatty acid. So if we have, 2 fatty acids that we can make a triglycerol from, then there's going to be, probably 3 different combinations for what can make a different triglycerol. Right, so we might have something where this is fatty acid 3, fatty acid 2, and this is going to be fatty acid 1. Right, and this would be an example of a natural triglyceride or triglycerol. So this is a simple representation for how we can represent the triglycerols. And this would be an arbitrary natural fatty acid, and then a synthetic one could be something where we have our glycerol, and they can all be the same fatty acid for each of them. They could be like oleic acid, oleic acid, and oleic acid. And this could be a synthetic. Triglyceride. Sorry?
Does one that we can make fatty acids in the body, so it's like proteins or amino acids where some we can't make, some we can?
Yeah, so there are certain fatty acids that you have to get from your diet. Those are essential fatty acids, right? So you need those to synthesize the different triglycerols and stuff that your body can use, right? So a lot of these are used for energy storage, and a lot of that energy storage is stored in these ester bonds. for these, and then they go through different. The reaction mechanism for the release of energy from a fatty acid is a lot more complicated than it is for carbohydrates, because that's just the glycosidic bonds for carbohydrates. For fatty acids, there's a lot more complicated reactions that can go on. It's a much longer metabolic pathway. And we'll talk about metabolic pathways probably in 2 weeks. But yeah, the same way you have essential fats and oils, right? Those are the same as the essential amino acids that your body can't make naturally. Okay. All right, so here we have an example of myristic acid. So if we have 3 of these, draw the triglyceride that forms between this and what would be the alcohol backbone for this triglyceride. What is it called? Glycerol, right? So glycerol, which was, I'm going to draw it in a different orientation, OH, H2C, H, CH2, OH, right? This is our glycerol. To draw the fatty acid, or not the fatty acid, the triglyceride that would form between these 4 molecules, right? And this is a condensation reaction. We start is we just start from drawing the glycerol, right? And then we have an O, which is going to be the alcohol side of our ester, right? And then that's bonded to what? How do we define that carbon in a aldehyde, ketone, carboxylic acid? It would be the carbonyl carbon, right? So this would be the carbonyl carbon, which is defined by the double bond to the oxygen. And then the identity of the fatty acid is given by what in this case? So the carboxyl group isn't going to define the fatty acid because that's going to be on all of our fatty acid. It's going to be defined by the nonpolar chain, right? Is it saturated, unsaturated? How many carbons are a part of it? That's what gives us the definition of the fatty acid. So then our triglyceride is just going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So technically 14 carbons total, right? And remember, fatty acids usually have an even number, lipids usually have an even number of carbon atoms. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I know right now it's tedious to do that, and eventually we'll move on to just using the kind of block diagram for drawing the fatty acids, but it's important to realize that this is what gives the triglyceride its identity. There's no real naming convention for the triglycerides because there's so many different combinations and permutations of them. All right, so we'll see in the next one that if you have, 3 different fatty acids, then you have 3 factorial different ways of combining those, each in a unique spot. Or sorry, not 3 factorial, you have 3 squared. You have 9 different ways of making a fatty acid. All right, so that makes sense to everyone? Esterification, we're forming an ester bond from an alcohol and a carboxylic acid. And usually what's required for this reaction to happen? Does anyone remember? Water is going to be one of the byproducts, right? Because there's going to be a water for each of the ester bonds that we create. Usually requires some sort of acidic conditions for this to happen. Or some sort of catalyst if you don't have the acidic conditions. Okay, so here we have 3 different, sorry, was anyone still looking at the previous slide? So the next slide we're going to have 3 different fatty acids and you're going to want to come up with one triglyceride you can make from those 3 fatty acids. And you'll see why natural fatty acids, there's really no preference. They're usually going to have different fatty acids at every spot, right? So you imagine that you have these 3 fatty acids floating around in solution. There's going to be 9 different ways that you can make a triglyceride from that. So come up with one triglyceride based off of these 3 fatty acids. You see there probably is some restrictions in them, but the ester bond isn't, that can rotate that bond. So even if you have a big bent molecule like that, that can just rotate out of the plane of the other fatty acids to all fit in the same part, right? So we start from the same spot where we have what molecule holds all of the fatty acid parts of the triglyceride together? The glycerol, H2C, HC, H2C, like that. And then you can put any fatty acid in each spot. Functional group we're going to have before we draw our long nonpolar chain. Ester, right? Because triglycerides have an ester formed with a trihydroxy alcohol. So the carboxylic acid of the fatty acid and ester, or the alcohol of the trihydroxy alcohol, come together to form the ester functional group. So each of these are going to have ester. And then who wants to give me one of the acids to put in the first spot? Which one? Top left, top right, or bottom?
Top left.
Top left, okay. Any reason for that one? All right, so that one has 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And so it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. So I curved up like that, but because the ester bonds aren't, sp2 hybridized, right? That is sp3, technically oxygen there. We didn't really talk about hybridization of oxygen, but that bond can rotate, so that alcohol can rotate out of the way to fit the other fatty acids, or that ester bond can rotate to get that fatty acid group away from the other fatty acids. And what about the next one? Which one do you guys want to do? Top left, top right. You're going to choose Jesus because you chose you chose the first, unless anyone is opposed to Jesus choosing.
Top right.
All right, so we'll do that one. So that one's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 1, 2, 3, 4, 5, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's your second one, and then I'm going to choose the last one, and I'm going to choose that one again because it's the easiest to draw. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right, so we can have multiple of the same fatty acids, even in a natural fatty acid, but the chance of having all 3 of them in the same spot is very low. So that's why most naturally occurring triglycerides don't have the same amino acid. All right, so that's how we would, given a set of 3 molecules, choose a triglyceride to draw from them. The main idea again here is the formation of the ester, right, functional group from the trihydroxy alcohol and the carboxylic acid group. Okay, any questions on this? No question? Okay, so then we'll wrap up triglycerides, and then on Monday we'll talk about the other types of lipids, and so complex lipids and non-saponifiable lipids, which were sphingolipids and steroids. So we'll talk about those on Monday, and then we'll wrap up lipids there and start talking about nucleic acids, which is DNA, RNA, and stuff next week. But first, we have to talk about the reactions of fats and oils. So we can use an acid the same way we can make an esterification in acidic conditions. We can use an acid to cleave the esters, and this performs what kind of reaction? If we cleave the ester into what 2 groups whenever we break up an ester? Carboxylic acid and alcohol, right? It's just the opposite of what we just did, right? And that was called what type of reaction if it's acid catalyzed? Hydrolysis, no, it is hydrolysis. Base catalyzed is called, so this was a hydrolysis reaction, right? And base catalyzed hydrolysis specifically is called saponification, right? So that was the saponification reaction. Reaction. And then we can also, so we can, we're can bring back another reaction, all the way back from alkenes. We can go from a saturated or an unsaturated fatty acid to a saturated one through reaction. And so if we're going from unsaturated to saturated, what are we eliminating and what are we adding to the molecule? Yep, we're adding hydrogens and eliminating. It wouldn't be oxygen, right? Because remember, we did this when we went from alkenes to alkanes, way back probably the second week of class. Right, went from alkenes to alkanes, right? An alkene is classified by what? A double bond, right? And so then we went to an alkane, which has only, right? So what are we breaking between those two? Yep, we're breaking the double bond, right? So we're getting rid of the alkene, the double bonds, and adding hydrogen in their place. So we add hydrogen and minus carbon-carbon bonds, right? And does anyone remember what this type of reaction was called? Right, where it has to do with what we're adding. We're adding what to the molecule? Hydrogen, right? So does anyone remember what it was called? Hydrogenation, right? Or hydrogenation, same thing, right? It's just pronounced a little bit differently, right? So this was a hydrogenation reaction. And so the way a hydrolysis worked, if we had an arbitrary ester, right, we had two R groups. What do we need to consume in a hydrolysis reaction? Water, right? Because we need to add an OH group and a proton in there somewhere so that we end up with a carboxylic acid and an alcohol. So we add water in the presence of H plus acid, and we create an alcohol and a carboxylic acid. Right, and we have to consume water for that reaction to happen. So that was the general form for hydrolysis. Using a basic condition is the saponification reaction. And so it's the same idea. We start with an ester. We can put the carbonyl facing down here, R prime. And what do we have to consume in this reaction? So it'll still be water. Oops. And then we're going to have OH minus, which is catalyzing the reaction. So it's catalyzing, so we're going to have to regenerate OH minus in this reaction. We're going to have our alcohol plus, and then what do we get as our other molecule in basic conditions? Right. It'll be half the salt, right? So it'll be the carboxylate ion. It won't be a carboxylic acid. It'll form O minus C double bond O, R prime, right? And then we have base regenerated, right? So basically what happens is we're going to donate one hydroxide to this molecule and we'll be consuming the full water, and then base is going to be regenerated from that reaction. In the general form for a hydrogenation reaction is if we have an alkene, we add hydrogen gas, right? And then what do we, does anyone remember what we need for the conditions for that? This was, we needed to catalyze this reaction, and it was a metal catalyst. Which one? That's the very oxidizing agent. So that's a very strong oxidizing agent. So here we're not going to be oxidizing. If anything, we're reducing because we're adding carbon-hydrogen bonds. So you could probably do it with lithium and aluminum hydroxide or sodium borohydride. But it was just nickel or platinum was a metal, right? So it was Ni or platinum catalyst, right? So if you have this metal in solution, this will happen readily. And this goes to R prime, and then we just add a hydrogen. Hydrogen's across where the double bond was. So that's just a general reaction pathway, just kind of what is the products given these reactants. We have an ester. We want to predict the product. We go to alcohol carboxylic acid when we do any type of hydrolysis, either saponification, which is base catalyzed, or just regular hydrolysis, which is acid catalyzed, or hydrogenation reaction of an alkene. And so, I'm good to go to the next slide? All right, so for this, we have an arbitrary, I don't know what kind of molecule this is. Looks different than what I've been drawing, but. It almost looks like a peptide, right? So this is actually, right here, if we look at it, this looks like our glycerol, right? That's been esterified with 3 different fatty acids right there, right? So this is, remember, it's like, well, how do they all fit in the same side? This is what an orientation that you could have where all the fatty acid groups are facing far away from each other. Now this looks more like something that you'd actually see floating around in solution, right? Where these bonds, they're single bonds, they can rotate and point things away from each other, right? So this is an example of a triglyceride that I made up. And if we're going to go through acid catalyzed hydrolysis, acid catalyzed hydrolysis, that means you need to consume, if we were to write out a reaction for this, all right, so we'll just put the reactants on the top because we're probably going to run out of room otherwise. Reactants, and then products down here. So we have H plus as our reaction arrow here. And then what else do we need on the reactant side here? Water, right? And how many water molecules do we need? 3, right? So triglycerides need 3 water molecules. And then what are our products going to be for this reaction? And what, yeah, but specifically which alcohol is going to be our product? No, not the classification of the alcohol, but like when looking at this, because we've been talking about the alcohol, so that's why I asked. Glycerol? It'll be glycerol, right? Because this glycerol sequentially, which means not all in one step, is going to be hydrolyzed, right? So every fatty acid is going to be sequentially hydrolyzed from this glycerol molecule. And in the end, you're just going to have the glycerol. And so we can draw the glycerol like how it's drawn here. OH, OH, OH. Right, so I kind of drew that in the same orientation as the triglycerides ester kind of vertex is what I call it, because all the fatty acids look like they're coming together. And then we're going to have how many different fatty acids? 3, right? Because we have 3 different fatty acids here. We know we have 3 different fatty acids because this is one of the nonpolar side chains, this is another one of the nonpolar side chains, and this is another one. You can tell this is probably not a real fatty acid. It's just something that I made up because it's a very short nonpolar chain, and I didn't feel like making very long molecules to go through these examples, right? But these could, in theory, be going out for very, very long, 18 long carbon chains, right? And so we'll have and I'll color coordinate them, this carboxylic acid, right, which is going to be that fatty acid in the triglyceride there. Then we'll have this other simple one, which will be another carboxylic acid. And this is just a small side chain there. And then the last one, which would be another, and would this be a saturated or an unsaturated fatty acid, this last red one? Does it have any double bonds in the polar chain? Yep, so it would be unsaturated, right? So this will be unsaturated. All right, so that would be our products for this reaction, for the hydrolysis here. And then I'm going to copy all of this for the next slide. copy. So am I good to go to the next one, or are people still writing the products? I know this is a lot of writing for this one, for these molecules, right? So when we did, esterification and hydrolysis before, simple R groups and stuff like this, biomolecules, the same reaction is going on. It's just the molecules are a lot bigger usually, look a lot different. And kind of thing that I want you guys to realize is that, even if the molecule looks big and scary, it's the same fundamental idea that's going on between these two. So here we have saponification. And so just looking at the previous page, what's going to be different from this page to the saponification? Or what are some differences that you think you'll see? All right, saponification, we have basic conditions. So what should the protonation state of the carboxylic acid be? It should be deprotonated, right? So instead of a bunch of carboxylic acids, we should have a bunch of carboxylate ions. Let's see if I can copy and paste all of this. Get it to line up nicely. So it's the exact same thing, except instead of H+, we have what catalyzing the reaction? OH-, right? And then we just erase all of the protons off of the carboxylic acid hydroxy group, and we just add a negative charge for each of them. All right, so that's the only difference between saponification and acid catalyzed hydrolysis. And so this is useful for making soap, right? Because then we add some counter ion like sodium, calcium, something like that, to then make our fatty acid salt. All right, so we can take a triglyceride, hydrolyze it, fatty acid, salt, fatty acids are a product of that. Carboxylate ion is a product if it's base catalyzed, add counter ions, and then we get our soap. Okay. I'll leave this up for a second, so then I'll just talk about the next slide while you guys are still writing this down. All right. Am I good to go to the next slide? All right. So for hydrogenation, what are the conditions for hydrogenation? What do we need to bubble into the solution? Hydrogen gas. And then these will be our reactants. And then what's our catalyst going to be? Which one do you guys want to use? Nickel. We use nickel as our catalyst. And then our product is basically we're going to go through at every double bond here, which are just these two, our carbon-carbon double bonds, and we're just going to replace those with hydrogens in that molecule. So this is going to be O, like that. And so we've gotten rid of all the double bonds. I'm going to draw the hydrogens, even though you don't have to, just to highlight where we replaced the double bonds with hydrogen in that molecule. And now you see that we have a fatty acid that is a triglyceride that has all the same fatty acid, right? Because even though there were saturated and unsaturated versions or fatty acids before, once we made it saturated, they all had the same length carbon chain, so now they have 3 of the same fatty acids there.